Good morning. In today's digital world, your data is constantly being stored, shared, and analyzed. But have you ever wondered what happens to it while it is being used? We encrypt data when it is stored, we encrypt it when it is sent. But when it's time to process it, we usually have to decrypt it first, and that's when it's most vulnerable. What if there was a way to perform calculations on your data without ever unlocking it? That's exactly what homomorphic encryption makes possible. In this video, we'll explore how this breakthrough works. From the basics of encryption to the magic of homomorphism, to the different types like the partial, somewhat, and fully homomorphic encryption. We'll also dive into real world examples in banking, healthcare, telecom, AI, and more. So you can see how it's transforming privacy and compliance. Whether you are a student or a cybersecurity professional or a business leader, understanding homomorphic encryption is no longer optional. It's a glimpse into the future of secure data processing. With special thanks to Natesh, Shobha, Shakti, and Varat, this is your host, Savit Vittal Salian. Namaskar. Join me as we unlock the secret of keeping your data safe when it's in use. Let's start with something that we see generally in our daily working. Today or now we get these type of ready to cook meals which comes in a packet, a silver packet, foil. We take it and we know what that product is. It could be your local delicacy. In India, it could be butter chicken, paneer butter masala, on or steamed rice, jeera rice, things that we like. So instead of bringing each ingredient together, what we do is we get the packet which has all the right ingredients in the right quantity. We get that packet, we put this into a bowl of water and heat the water. Once you do that, in 5 or 10 minutes time, the water boils and it cooks the whole packet. And in 15 minutes time, you generally have the food ready. In this, we don't have to know what was the quantity used, what was the product, how much of a paneer, how much of a chicken, how much of a masalas were, in what quantity, in what proportion were used. We just bring the whole packet, boil the whole packet, and we have a ready material. So we can enjoy it. Today's topic is very much like that. That's an analogy on how homomorphic encryption works. So think of cooking with a sealed packet. You can mix, shake, or heat the sealed packet without opening it. And when you finally open them, the contents have changed exactly as they would have if you had mixed it or cooked them openly. But you never saw the raw ingredient. So that's a simple analogy on what homomorphism is all about. Let's start the journey. This is your host Savit Vittal Salian. Today we will enter the territory of homomorphic encryption. We'll try to understand it. Let's enjoy it. Do note, this technology is developing. So while you might have not seen its full implementation, and that is not because it doesn't have a practical use, it has, but on ground it is still under development. But then it's good to know what's coming and prepare accordingly. So this whole video is a crystal ball to see how things are going to be potentially in future. Our agenda: let's look at the fundamentals and background of homomorphic encryptions. Well, in an increasing digital world, the volume of sensitive information handled by organization has reached unprecedented levels. From financial transactions to healthcare records, and from government census data to AI training data sets, data fuels modern innovation. Yet, with this data comes the paramount responsibility of protecting it from misuse, theft, or unauthorized access. Traditional encryption, such as AES, RSA, and ECC, has long served as the primary defense mechanism. These systems convert plain text into unreadable ciphertext, ensuring that only holders of the correct decryption key can recover the original information. While highly effective in securing data at rest and in transit, traditional encryption suffers from a fundamental limitation. To process the data, it must first decrypt. This decryption step exposes the data to potential threats, whether from compromised systems or insider misuse or vulnerabilities in the computing environment. Now let's go to the basics. What is encryption? Encryption is the process of transforming readable data or plain text data into a unreadable form, also known as ciphertext, using a mathematical algorithms and a key. Purpose: to protect confidentiality, ensure that only authorized parties can read the information. The traditional method, data must be decrypted before processing. This exposes it to a risk. In other words, what's encryption? Well, encryption is like locking your information in a special safe so that only someone with the right key can open it and read it. When you encrypt something, you turn it from normal readable form into a scrambled unreadable form. When you decrypt it, you turn it back into its original form using a secret key. Think of sending a letter example. Without encryption, well, you write your letter in plain English, put it in an envelope, and send it. Anyone who opens the envelope can read it. But with encryption, you write your letter, then you use a secret code that changes every letter into symbol. Now, even if someone opens the envelope, they see only gibberish unless they know the code to turn it back. Now let's take a digital example. We all know or use WhatsApp. So when you send a message, it is encrypted before leaving your phone. Only the receiver's phone can decrypt it. Even WhatsApp servers can't read the message. Let's take online shopping. When you enter your credit card number on Amazon, your browser encrypts it before sending it to the server. This prevents hackers from stealing your details during transmissions. Or let's take laptop security. If your laptop uses disk encryption, even if someone steals it, they can't read your file without your password. So, encryption doesn't stop someone from getting the encrypted data. It just makes sure they can't understand it without the right key. Homomorphic encryption addresses the limitation of traditional encryption by enabling computation directly on the encrypted data. With homomorphic encryption, the data remains encrypted throughout the life cycle, during storage or transmission, and also during processing. And only the final results is decrypted. This breakthrough offers an unprecedented balance between utility and privacy, making it particularly relevant in regulated and high trust industries like BFSI or healthcare and government. So, where homomorphic encryption fits? Well, homomorphic encryption is a privacy preserving cryptographic technique that allows computation to be performed directly on encrypted data without decrypting it. The result of computation, when decrypted, matches the outcome as if it has been performed on the original plain text. The key advantage? Well, you don't need to expose sensitive data during processing. It's critical for, say, secure cloud computation or AI ML or compliance driven industries. Well, think of the three main stages of data. At rest, that's when the data is stored, could be in hard drive or in cloud or etc. Or in transit, when it is sent over a network, could be your email or API calls etc. Or when in use, or when you're processing it or analyzing it. Traditional encryption protects data at rest and in transit, but not during its use. When you process data, it usually needs to be decrypted first, which is where it gets exposed to potential risks. Now, here, homomorphic encryption fills this gap. It keeps data encrypted even while it's being used for computation. This means sensitive data stays protected at every stage. Analogy: imagine a locked lunchbox. With normal encryption, you must unlock it to eat, and anyone nearby could see what's inside. Now, with homographic encryption, you can stir, cut, or mix food through special gloves without unlocking the lunchbox. Only at the very end do you unlock it to eat, and the food is ready exactly as you want it. We discussed the original idea when we started this video. The packet food ready to eat. Let's take industry examples. The banking. Two banks wants to check for duplicate loan applications. With homomorphic encryption, they can compare the encrypted customer data without sharing the actual names or IDs. Healthcare. Hospitals can send encrypted plain test results to a research lab. The lab can run its analysis without ever seeing the raw medical data, but returning only the encrypted results. In the cloud AI services, a company encrypts its customer data before uploading it to the cloud AI model. The AI processes the encrypted data and returns an encrypted prediction. And then the company can decrypt the results locally. So other than the company, the whole process do not require decryption, but they can process the whole content. So when the data has left the company, it was encrypted. The rest of all of the activities done by a provider was done on that encrypted material without ever decrypting it. And the results were also encrypted, sent back to the original company, and the company who owns that data would now decrypt it to know the results. No one else knows what really was there at the original content. So, homomorphic encryption is a extra protection for data in use, solving a security gap that traditional encryption leaves open. Let's look at the concept. In mathematics, a homomorphism is a structure preserving map between two algebraic structures. Example, addition in plain text maps to addition in ciphertext. Example, if encryption A and encryption B, two different datas, are encrypted values, or A and B are encrypted. In addition, what would happen is you would decrypt both this encryption as A plus B. In multiplication, you would decrypt the encryption A into encryption B as A into B. So now if you see this logic, you are decrypting the whole together. But then in itself, the A and B are encrypted. You don't know the content there. You are adding both the encryptions together, not A and B. You are adding the encrypted A and encrypted B to get the result. Similarly, you are multiplying the encrypted A and encrypted B, not A and B. This property allows secure processing of encrypted data. Let's go with few more examples. In mathematics, a homomorphism is a fancy word for transformation or mapping that keeps the rules of the game same. So when you perform an operation, whether it is addition or multiplication, before or after the transformation, you get the same final answers. Let's go back to the earlier slide. So if you had added A and B without encryption, you would have got the value of A and B. Similarly, if you encrypted A and encrypted B and then you add it, you will still get the same result. Similarly for multiplication. So by encryption, you are not contaminating or changing the final results. The result remains the same. But no one else would know other than the one who has encrypted what the actual A and B are. But the results would still be the same. So in encryption, homomorphic encryption means you can do certain calculations on encrypted data, and after decrypting the results, it will be the same as if you had done those calculations on the original unencrypted data. Now do note, important is certain. At this point of time, as I said in my introduction, this is developing technology. So there are certain limitations on how much it can be done practically on ground, what type of calculations can be done. This stage, addition, deletion, minus, multiplications, some very basic levels can be done. Yes, there are few advances. We'll discuss that as we move forward. So as an example, say let's take a basic math example. So you have two numbers, 5 and 3. You encrypt them. You encrypted 5 and you encrypted 3. You add the encrypted value. What you get is an encrypted 8. So when you decrypt, you get 8. You have now decrypted the output, which is the encrypted 8, not the encrypted 5 or 3, not the addition. You have encrypted the end result, which is 8. Now think through whether if it had not been encrypted, it's exactly the same as if you had added 5 and 3 before encrypting. The same is true with multiplication. Suppose you encrypt 5 and you encrypted 3. If you had multiplied both this encryption, you still get 5 into 3, which is 15 in encrypted format. So when you decrypt the result, you get 15. That's how homomorphic encryption works. The whole idea is to secure the original content, and the final result does not change because of that. You add value, either it is plus, minus, or multiplication. Add value, you get a result. The result is also encrypted, and then you get a decrypted value. That's the objective. Let's take example from banking. Two banks encrypt their customer transactions total. They can add these encrypted totals together to get the combined total without ever revealing each bank's individual numbers. Healthcare. Well, hospitals encrypt patient stats. They can combine the encrypted data to get an overall stats without exposing any single patient's data. There are three types of homomorphic encryption: partial, somewhat, and fully homomorphic encryptions. Partial. Well, this supports only one type of operation. It could be either addition or multiplication. Example, your RSA. RSA is multiple logic used. For its example case for a multiplication, multiplicative. Then you have a Pillier, which is additive, addition. In somewhat homomorphic encryption, or SHE, It supports both addition and multiplication, but with limited complexity, that is number of operations. Now do note, you can multiply once, or you can add once, or you can add it multiple times, more than one, 3 times or 4 times or 6 times. So that's what somewhat homomorphic encryption means. You can have some limited complexity here. Fully homomorphic encryption, well, it supports unlimited addition and multiplication on ciphertext. It's considered the holy grail of privacy reserving computation. The first fully homomorphic encryption scheme was proposed by Craig Gentry in 2009. It's pretty long that the developments are going on this subject. Let's look at partial homomorphic encryption. It means it supports only one type of mathematical operation. It could be either addition or multiplication on an encrypted data. So it's either, not both. You can do that operation as many times as you want, but you can't mix it with other ones. So if you are doing addition, you can do addition multiple times there. If you're doing multiplication, you can do that multiple times. But you can't have addition and multiplication together. It won't work. So that's partial homomorphic encryption. Example, if a scheme supports only addition, example as is shown, encrypting 5, adding that to an encrypted 3 would give you 8. It will work. But then if you are mixing it, it won't make sense. Real world, let's look at the failure encryption, which is primarily an addition area. You securely adding encrypted vote count in electronic voting without revealing the individual votes. This is an example that has been given. So you have votes coming in, you encrypt it, and you add all the votes, and you would never know if, because you are not decrypting it, the original value, you never know which area has provided what votes to whom, because it is encrypted. So that's your failure encryption. When you come to RSA encryption, which is primarily a multiplication phase, this is where you securely verifying your digital signature. So that's, now you know about RSA and one aspect of it. It's actually using homomorphic encryption, but categorized as partial. Let's look at somewhat homomorphic encryption, or SHE, meaning it supports both addition and multiplication, but only for a limited number of operations. After a certain point, the encrypted data becomes too noisy and can't be decrypted correctly. Example, you might be able to do a encryption 5 plus encryption 3 into encryption 2, that to a few times in a row. But if you keep adding and multiplying over and over, the result will break, it will get corrupted. Real world use, well, privacy preserving statistics. Example, a government agency might run limited computation on encrypted census data, like adding income and multiplying by tax rate, without decrypting the raw data. This is a example potentially can be used or already used in real world. So that's SHE, or somewhat homomorphic encryption. Let's look at fully homomorphic encryption or FHE, meaning it supports addition and multiplication on encrypted data, but you can run complete programs and complex analytics without ever decrypting the data. It uses a process called as bootstrapping to clean the data and keep it usable forever. Do remember what happened in She? In She, you can do after a certain point, it will become noisy and you can't decrypt it. But in FHE, you can do that multiple times over time because bootstrapping cleans out the noise, helping it to keep it reasonably okay so that you get a reasonably accurate information. Example, you can do an addition, you can do a multiplication, then you can add it, then you can minus it, and so on with no limits. Real world use, the cloud AI services. A hospital encrypts patient records and sends them to a cloud AI model for diagnosis and can get back encrypted result. The data is never decrypted in the cloud. That's because in the cloud there could be multiple similar data coming on from hospitals, which would require a combination of it for research. For research, it might require multiple inputs from multiple hospitals coming together, requiring multiple steps of addition, deletion, multiplication, division. So basically, this gives you that leverage. So in summary, PHE it supports addition or multiplication with the limitation that only one operation types are allowed. In SHE, both addition and multiplications are allowed. It's limited number of operations can be performed in this combination. In FHE, both addition and multiplication are allowed, similar to SHE, but there are no limit on the operations. So now why homomorphic encryption matters? Well, security in untrusted environment, which is enables cloud services to process client data without ever seeing the raw data. That's the first. Second is regulatory compliance. It helps to align with the privacy mandates like GDPR, HIPAA, DPDP Act by minimizing the exposure of sensitive information. Third is it provides business advantage. It helps to unlock collaboration opportunities without data sharing in raw forms. That is between banks for fraud detection as an example. Advantages are huge. You can think through on your space in your industry how this can help. While most encryption today protects data when it's stored or at rest or sent, the problem is to use the data, you have to decrypt it first, which exposes it to risk. So, homomorphic encryption solves this gap by letting you work on your data while it's still encrypted. So, there is no moment of exposure. Why it's important? Well, it protects the data even in untrusted environment. It helps with privacy laws and compliance. It enables safe collaboration between organizations. Let's go a little deeper into this. Well, you can send encrypted data to a cloud or a partner organization and they can process it without ever seeing the actual data. Example, a bank sends encrypted transaction records to a fraud detection services in the cloud. The services flags suspicious activity but never actually sees a single real transaction. So that's protecting the data in an untrusted environment. Next is laws like GDPR, HIPAA, and India's DPDP Act require minimization of who can see personal data. Homomorphic encryption ensures even your own service providers or analysts don't have any direct access to the raw data. Example, a hospital encrypts a patient's lab result before sharing them with a research lab. The research lab analyzes the trend without ever seeing individual patient names or its results, thus helping you with the privacy laws and the required compliances. Think through the protection it is providing you today, and with the introduction of homomorphic encryption, what a giant leap it would be in this space. The next is collaboration. Well, computing companies or competing companies can work together without sharing the trade secret. Example, two retailers encrypt their sales data but run a joint analysis to predict seasonal demands. They both see the forecast but would never see each other's raw sales numbers. So, homomorphic encryption matters because it closes the last big security gap, which is data in use, while unlocking new possibilities for secure, privacy respecting collaborations. Let's take a look at how homomorphic encryption evolved over the period. It started off with 1978. Rivest, Edelman, Detroit introduced the concept of homomorphism. It was only in 2009 Craig Gentry published the first practical full homomorphic encryption scheme using lattice based cryptography. Then in 2010 and 2015, in between, optimization makes FHE faster. In 2016 till now, industrial adoption has grown, whether it is Microsoft Seal or IBM Ellipse or Google. They join and compute. Today, homomorphic encryption is a research and commercial focus, especially for AI on encrypted data. It's still evolving as we speak. It is yet to be practical. It is on the path, on the way towards it, and rightly so, because the time has arrived. As we know about the current encryption, though strong but not strong enough with the computing power that is available now to break it, and with a potential in future coming in from quantum computing, it can be broken much easier using computing technologies from quantum space. So the time has potentially arrived. Developments are aggressively going on the ground. Let's do a deep dive. So, how does homomorphic encryption work? Well, at its core, homomorphic encryption is about designing encryption schemes where mathematical operation on ciphertext correspond to the same operation on plain text. So the design is not to corrupt the output. You should ideally get the same result if you are doing without encryption as you do with encryption. So basic flow works like this. There's key generation where it generates a public or private key pairs. You have encryption where you convert the plain text into ciphertext using public keys. Then you do computation on the ciphertext where you perform either addition, multiplication, or both, or other supported operation without decrypting the content. And finally, once you get the output, you use the private key to retrieve the final result, which would match the computation if it is done without encryption or on plain text. So you are decrypting the result, the final result, not individual content. Example, plain text, x is equal to 4 say or y is 5. When you encrypt, it becomes encrypted 4, encrypted 5. When you compute, whether your addition 4 plus 5 encrypted would give you a value of encrypted 9, which would very similar if you had not done an encryption. Only thing is, if you had not done it, everyone would know what the original value is. But because you have encrypted, no one would know what the original value was, which is 4 and 5, and what the final value was. But only the one who is supposed to know would decrypt the final value, not the individual. The final value and get the value, in this case 9. I hope this helps with a little better perspective. Let's look at a mathematical principle behind homomorphic encryption. Most practical homomorphic encryption schemes rely on lattice based cryptography, particularly the learning with error problem or LWE. It's a hard problem believed to be secure against quantum attacks. What's quantum attack? Well, with the current encryption, with certain effort, you can crack it using technologies as such. But when quantum computing takes its role fully, the immense power that quantum computing brings to the table, breaking this encryption should be easier compared to the current without using quantum. So the challenge towards that quantum attack is your homomorphic encryption. At least that's how it is seen today. And that's where the evaluations are going on. The key idea is noise introduction. Well, every encryption adds a small amount of noise to secure the message. Operation increases noise if it grows too large and the decryption would fail. Now, in homomorphic encryption, there is a concept of bootstrapping. It's a technique to refresh the ciphertext and reduce the noise, thus allowing unlimited operation. So, without bootstrapping, which is homomorphic specific concept, with ciphertext you do encryption, you do your calculation. Every time you do it, a small amount of noise gets added. As you increase your computation on those, the noise gets added, and finally the output you can't get it because it is totally corrupted. To navigate this, bootstrapping helps to clean up the ciphertext, does a refresh so that you can continue your processing over and over again. That's an advantage. That's a concept which is helping homomorphic encryption scale higher. It cleans the noise to some extent, yes. Now, why lattice was used? Well, from an hardness perspective, it's about finding the shortest vector in a high dimension lattice is computationally infeasible for both classical and quantum computers. So, if you want to break it up, lattice is complex enough to an extent that it is identified that it is computationally infeasible. Leave the traditional, even quantum computing at this point of time would not be able to break it, or it is extremely difficult to break it. From a noise perspective, a small intentional error is added during encryption to secure the plain text. This noise grows with computation, limiting SHE but addressed in FHE with bootstrapping. So lattice helps you provide that flexibility or advantage by cleaning off those noises. That's why lattice is used. Now let's see what is bootstrapping. Bootstrapping is the process of homomorphically refreshing a ciphertext to reduce its noise levels, enabling future computations. Analogy: imagine a blurry photograph that becomes blurrier with each copy. You have potentially experienced this in your own life. Bootstrapping is like restoring it to the original clarity. A normal one, you would say that clean up the image, it's not clear. So using tools and techniques that's available to you, you would potentially clean it up. So while enabling unlimited computation, it's computationally expensive. Though recent research has significantly reduced the cost, the trade-off is it requires a lot of investment. Having said that, the concept of bootstrapping is what gives an edge to homomorphic encryption. Let's revisit a few of the categories in the homomorphic encryption schemes. If it is RSA, it's a PHE, partial homomorphic encryption. Here, operation support is only multiplication, primarily used in digital signature or secure multiplications. If it is PILIA, it is again partial. But in this case, only addition operations are used. Example, we said secure voting or aggregated statistics area. Then we have the Berkshire Gentry Vaikunthanathan or BGV, which is full homomorphic encryptions. It supports addition and multiplication. Then we have Berkshire and Van Berkunter or BFV. It supports full homomorphic encryption, supports addition and multiplication. Then we have Chon Kim Song scheme, which supports approximate full homomorphic encryption. It supports addition and multiplication on approximate value, generally used in machine learning or signal processing. Then we have fast fully homomorphic encryption over the torus or TFHE. It's a full homomorphic encryption, provides fast bootstrapping and Boolean gates. This is used typically in real-time encrypted processing. RSA. The RSA algorithm is one of the oldest and the most widely used encryption methods. It's mainly known for secure communication and digital signature, but it is also has a partial homomorphic property. It supports multiplication on encrypted data. Not many know about this. Now you do. So how it works? Starts with you create a public key and a private key. Then a message is turned into a ciphertext using the public key. and a mathematical formula is used. Now if you multiply two ciphertext, it's the same as multiplying the plain text and then encrypting the result. Let's say encrypt 5 is the encryption of 5 and same 3 is for encryption of 3. Now with RSA, if you multiply encrypted 5 into encrypted 3, you get a new ciphertext which is encrypt 15. So when you decrypt it, you get 15, the product of the original, if you have done the same thing on plain text number. So that's how it works on the ground from an RSA perspective. Scenario: a company stores employee salaries encrypted with RSA. Now they need to calculate a bonus, that's a multiplication factor. For example, say salary into 1.1, but with the condition without decrypting individual salaries. So what they do, they encrypt the salaries with RSA. They multiply the encrypted salary value by the encrypted bonus factor. The bonus factor is also encrypted. So salaries are encrypted, bonuses numbers are encrypted, and they multiply both. What's done? They decrypt the final results to get the updated salaries without ever exposing the original salaries in plain text. So no one would know what their original salary was, no one would know what the bonus factor was, but they would get a final number, and that when encrypted they would know what the numbers are, but the rest of the numbers are invisible or can't be known by other than those who had initially built it. Let's look at limitations. RSA's homomorphic property works only for multiplication, not for addition. It's not suitable for complex analytics where you need both the operations. It's less efficient than modern homomorphic encryption schemes for large scale data processing. So these are limitations. So RSA is a partially homomorphic. Great for secure multiplication, but not enough for full scale encrypted computation like full homomorphic encryption can do. Let's now look at the CKKS or approximate homomorphic encryption. The CKKS scheme allows operation on encrypted real numbers with controlled approximation, which is ideal for AI and statistical workload. Scenario: a hospital encrypts patients' cholesterol levels for sending them to cloud AI model. The cloud runs the regression analysis on ciphertext. Output: the encrypted prediction is sent back to the hospital. The hospital decrypts and uses the result without ever revealing patient's data to the cloud provider. Pretty straightforward because now we know the background and how this logic works. Let's look at from efficiency and performance perspective. While full homomorphic encryption is secure, it's historically been slow and resource intensive. Challenges: well, large cipher size, big problem. It's 100x or 1000x larger than a plain text. It requires high computation, hence high cost. It requires a lot of memory and bandwidth. So that's the overhead. Now, what are the solutions developed? Well, there are hardware accelerators which are developed, and these are getting better and better on a daily basis. There are algorithmic improvements for better noise management. And there are hybrid approach, which is about combining the homomorphic encryption with secure multi-party computation. So these are under development. Now, widely used open source homomorphic encryption libraries include from Microsoft Seal, it supports BFE and CKKS. IBM supports BGV. Palisade supports multi-schemes for research and industries. And Concrete by Zama, it's a full homomorphic encryption for machine learning. You can look around this and try to get deeper into the subjects if you are interested of this is something which is in use in your area. Use cases and industry applications. Banking, financial services and insurance sector. Let's look at the challenge first. Banks and financial institutions often need to share or process sensitive customer and transaction data with third party analytics provider. This could be for fraud detection or for regulators. Traditional encryption requires decryption before processing, which introduces risk. With homomorphic encryption, it helps you to allow computation to be performed directly on encrypted data, thus ensuring confidentiality throughout the process. Example, two banks collaborate on fraud detection model without sharing the raw customer data. Using Pillar or CKKS schemes, they encrypt transaction patterns and jointly compute fraud probabilities. And only the final risk scores are decrypted by each bank. Benefit, it preserves customer privacy. It complies with GDPR or DPDP Act and RBI's data localization mandates. And it helps enable secure interbank collaborations. Let's look at healthcare. What are the challenges in this space? Well, hospitals, research institutions, and pharmaceutical companies need to analyze patient data for their research, for their AI diagnostics, or for clinical trials. But privacy laws restrict data sharing. With homomorphic encryption, it helps allow secure processing on encrypted health record by AI models without exposing identifiable information. Example, it supports multiple hospitals can encrypt patients' MRI scan statistics. A central AI service processes these encrypted values to detect early cancer patterns. But only the diagnosis results are decrypted by the hospitals. Benefit, it enables collaborative medical research wherein one hospital provides the data, the central services provide the processing, and then the results can be used by multiple organizations without actually revealing the individual client's or patient's information. Hence, it helps enable collaborative medical research. It maintains compliance with health privacy regulations, thus reducing the risk of data breaches during analysis. Let's now look at the telecom and IoT space. Well, telecom operators and IoT service provider handle massive streams of customer usage and sensor data. Analyzing this data in raw form risks violating privacy and security policies. With homomorphic encryption, it helps allows encrypted usage analytics, whether it could be bandwidth pattern, call duration, sensor metrics, or so on. That too without revealing the underlying individual, personal, or sensitive data. Example, IoT devices encrypt temperature, motion, and video metadata before sending it to the cloud. The cloud analytics detects anomalies, could be machine failure prediction, example, directly from the encrypted data. It helps improve trust in the smartphones and industrial IoTs. It also helps to meet telecom data protection obligations. And then it helps enable secure analytics at scale. Let's now look at AI and machine learning challenges. The AI ML model often require access to large data sets which may contain personal or proprietary information. Sharing this data risks leakage or IP theft. But with homomorphic encryption, it enables privacy preserving machine learning, where training or inference is performed on encrypted data. Example, a fintech company encrypts transaction data before sending it to cloud based ML model for fraud detection. The model processes encrypted data, could be using CKSS for numeric computation, but only encrypted outputs are returned, which are then decrypted locally. Benefit, it helps protect both the model owner's IP and the data owner's privacy, and enables cross organization AI collaboration without data exposure. Let's look at government and public sector space. Public agency often need to run statistical analysis across data sets from different departments without exposing sensitive records. Homomorphic encryption allows secure aggregation of encrypted data sets for policy analysis. Example, tax department and social service encrypt their respective citizen data sets. Aggregated encrypted computation identifies citizens eligible for benefits without sharing the raw records. Benefit, it enhances interagency cooperations. It complies with data protection mandates. And more, it prevents unauthorized data cross matching. Let's now look at e-commerce and retail space. Well, retailers need to perform joint marketing or supply chain optimization with partners without revealing sensitive customer or pricing data. With homomorphic encryption, it allows secure computation of joint demand forecast, price optimization, or customer behavior analysis on encrypted datasets. Example, two competing retailers would encrypt sales data of their own. Then a joint encrypted computation finds optimal stocking strategies without revealing individual sales records. Benefit, it enables secure partnerships and it protects competitive intelligence. Risk, challenges, and research trends. Let's look at performance bottlenecks. Despite huge advances since 2009, fully homomorphic encryption is still computationally expensive compared to plain text processing. The operation can be 100, 1000, 10,000 x slower than processing a plain text. So there is a computational overhead. It can be 100x or 1000x larger than the plain text from a cipher text size perspective, and it requires significant amount of storage and RAM processing for larger cipher text. Hence, there is significant requirement of memories or space. While mitigation efforts are going on, it could be hardware acceleration or optimized homomorphic encryption schemes, better computation processing technologies, or hybrid privacy, which is preserving computation. That is, we are combining with multi-party computation. That these are all evolving. These are all mitigation efforts which are being invested as we speak. Noise growth and bootstrapping. Well, what's noise? Well, random error added during encryption to make decryption hard without a key. Problem? Well, each operation increases the noise. If it exceeds a threshold, decryption would simply fail. Solution to this we discussed using bootstrapping. It's a technique to refresh the ciphertext by homomorphically decrypting it, but it's costly in computation. The next is security risk. Well, although homomorphic encryption is mathematically secured, practical risk remains, namely side channel attacks. It is exploiting timing, power, or memory access patterns, or weak key management, which is loss or leakage of private keys, can compromise all data. Or improper parameter setting, which is choosing parameters that are too small, can make homomorphic encryption vulnerable to attacks. So, the best practices recommended are isolating computation environments, using hardware security modules for key storage, or follow security parameter recommendation from standard bodies. Namely, homomorphic encryption.org is a good source for this reference. From a compliance and legal challenge perspective, there is no single global standard for homomorphic encryption at this point of time. So there is a lack of standardization. From a jurisdiction perspective, even if data is encrypted, some regulation treats ciphertext as personal data if it can be linked to an individual. From an audit difficulty perspective, proving compliance to regulator without revealing the actual data would be a big challenge. So we are not giving the actual data. How do you prove it to the auditor that you are in compliance in order for them to test? This is something that has been thought through. Currently, brainstorming sessions are there, or discussions are on board. Researchers, thinkers are working on this space. I'll keep you posted if there is progress noticed or declared. Yeah. Let's look at some of the research trends here. Well, quantum safe homomorphic encryption. Well, since most homomorphic encryption schemes are lattice based, they are naturally resistant to quantum attack. Research focuses on making them even more efficient. So now it is more about efficiency. The next is encrypted machine learning. Well, this is for optimizing the homomorphic encryption for deep learning workload. The next is in edge and IoT space. It's bringing homomorphic encryption computation to constrained devices. The next is standardization effort. The ISO 27 and homomorphicencryption.org are working on interoperability. Then we have cloud adoption. Major players are offering the homomorphic encryption enabled services now. Let's look at sector-wise benefit in comparison to traditional encryption versus the homomorphic encryption. Well, for BSI sector, the traditional encryption data must be decrypted for fraud scoring, exposing it to risk. With homomorphic, you can do this directly on the encrypted transaction, hence there is zero exposure. When it comes to healthcare, AI model requires plain text data, health data in traditional. Whereas with homomorphic, you can do that on encrypted patient data, thus preserving the privacy. In telecom and IoT, sensor data decrypted on cloud before analysis. With homomorphic, anomaly detections are performed on encrypted data. So basically, all of these sectors benefit from homomorphic encryption as it is all done on encrypted data sets. So what's the key takeaway? Well, from a functionality perspective, homomorphic encryption supports secure computation without revealing plain text. With partial, somewhat, and fully homomorphic variant for different needs. From a mathematical foundation perspective, it's built on hard lattice problems, offering quantum resistance. From an industry perspective, BFSI, healthcare, telecom, AI/ML, government, and retail stands to benefit from secure analytics and collaborations. Well, there are challenges, whether it's performance overhead, noise management, side channel risk, and lack of standardization. This remains barriers to mass adoption at this point of time. From a future outlook perspective, with hardware acceleration, optimized schemes, and cloud integration, homomorphic encryption is moving from research labs to commercial deployments. Let's now look at conclusions. Homomorphic encryption is transforming the way organizations think about data in use. It allows enterprise to process sensitive information without ever exposing it, thus enabling compliance, collaboration, and trust in ways traditional encryption cannot match. Homomorphic encryption has shifted the paradigm of data security from encrypt when idle to encrypt always. By enabling computation without exposure, it promises secure analytics, regulatory compliance, and unprecedented trust in collaborative data ecosystems. Homomorphic encryption represents one of the most promising advances in modern cryptography. Unlike traditional encryption, which requires decrypting data before processing, thus exposing it to risk, homomorphic encryption enables computation directly on encrypted data, thus preserving the confidentiality end to end. The road ahead involves tackling performance, standardization, and adoption barriers, but its trajectory points to homomorphic encryption becoming a standard tool for privacy in digital age. The technology is still evolving with performance, standardization, and adoption challenges ahead. But the trajectory is clear. In coming days, coming decades, years, homomorphic encryption will be the cornerstone of privacy preserving computing. With this, we have come to the end of this video. We started off with the introduction, we covered the fundamentals and background of homomorphic encryption, we looked at the technical deep dives, we looked at use cases and industry application, we looked at the risk, challenges and research trends, and then we looked at deliverables. I hope this video gave you a perspective on this space of homomorphic encryption. Do share it with anyone you think can benefit from this. This is for any student who wants to learn or know about the directions technology is taking. I'd like to thank you for the time that you have invested in this. Much appreciated. See you in the next video. Signing off, this is Savit Vittal Salian. Namaskar.